Hello, everyone. Today we'll discuss deviations from the ideal gas law. As we previously mentioned, a gas is considered ideal if its particles have negligible volume, if their volume is zero, and if there are no interactions between particles except for a perfectly elastic collision interaction type. So there are no intermolecular forces, there are no attractive forces, however, whatsoever between the particles. However, in a real gas, that is not so. So these assumptions are correct if a gas is at a high temperature and at a low pressure. However, if we do not fulfill these conditions, then there are deviations from this ideal gas state. So, the first assumption, assumption one, that there are no attractions between particles, fails if the temperature is too low. Why? Well, if the temperature is low, then particles don't have that much kinetic energy. They don't have that much speed. And in this case, there is a significant impact of intermolecular forces between particles because they slow them down. At high temperatures, they move so fast that the impact of intermolecular forces doesn't exist. But if they move slower, then it's a significant impact. And assumption two, that the volume of particles is negligible, fails at high pressures. Why? Well, we assume that at high pressures, a gas would get compressed. So the total volume of the space where the gas is in will be smaller, and then actually the size, the volume of the particles will be significant, a significant portion of that total volume. Now, at low temperature, here is what actually happens. So, as we said, lower temperature means lower speed of particles, which means that now there are interactions between them, and that slows the particles even more. And since it slows them even more, they will exert a lower pressure because if they're slower, then they're going to hit the walls of the container less frequently, or they're less likely to hit the wall of the container, which means that the pressure will actually be lower than for an ideal gas. And here you have a kind of an illustration of what happens when you when you increase the pressure and the volume gets smaller. You can see there here. I mean, this is obviously not the same gas, not the same number of particles. But what we want to illustrate here is look at this here, very high pressure. Actually, like 25 or maybe 15% of this container is red. So now the volume of the particles is actually a very significant part of this whole space. Now, this graph shows you what happens at lower or higher pressure. So why is there PV divided by nRT? Well, PV equals nRT. You know that's the ideal gas law. And then if you move nRT to the left side, PV divided by nRT for an ideal gas should equal 1. So this broken line is actually the ideal gas. So you can see that these real gases, CO2, N2, and helium, they are matching the ideal gas state at very low pressures, at pressures close to zero technically. But as you increase the pressure, they deviate from the ideal gas state. And you can see first, at least CO2 and nitrogen, they go below the line. Because as you increase the pressure, the first thing that happens is that the attractions between molecules start to have an impact. So we say that the attractions dominate. And then after a while, the lines go above the ideal gas state, which means that now the particle volume dominates. And you can also see one more interesting thing is that helium is the closest to the ideal gas state. Why? Well, helium has very small particles, so it doesn't go too high up. And in helium, there are very weak attractive London dispersion forces between particles. So helium is actually the closest to the ideal gas that you can get. I mean, at least as far as this graph is considered. And here see the overview of those same things that we just mentioned. So intermolecular forces impact the deviation from the ideal gas state. So the stronger the intermolecular forces, the more that gas will deviate from the ideal gas state. And here, remember, we're not here talking about ionic or metallic compounds. We're mostly talking here, so here speaking about hydrogen bonding, dipole-dipole, and London dispersion. So the stronger these forces in a specific molecule, the more it will deviate from the ideal gas state. And then don't get confused by CO2 here next to the word polar. So CO2 as a molecule, of course, is not polar because it's linear, it's symmetrical. However, inside of it, you do have two polar bonds. That has an impact on intermolecular forces. And also, CO2 is a pretty large molecule with a relatively high number of electrons. So even London dispersion forces between two CO2 molecules is still going to be they're going to be significant. And also molecular size. So the smaller the molecule, the more likely it is to align more with the ideal gas state. But if the molecule is bigger, then its volume is more significant and less it will align with the ideal gas state. Now let's take a look at some examples. Okay, state which assumption of the ideal gas model has broken down in these two cases. So this is a typical, very typical wording for AP questions. So we have here ammonia at 2 atmospheres and minus 30 degrees Celsius. So 2 atmospheres for a human is a pretty high pressure, but for a gas it's not. However, minus 30 degrees Celsius is a pretty low temperature. So what did we say? At low temperatures, the attraction between particles dominates. So that assumption fails. So now there are attractions between particles, so that assumption is not correct. And the second B is helium is compressed to 500 atms at room temperature. So 500 atms is a huge pressure for anything. So at high pressures, as we said, the particle volume is no longer negligible. Chlorine gas is held at a temperature only slightly above boiling point. Is the pressure measured in the container greater than, less than, or equal to the predicted pressure of the ideal gas? So, as we said, if you lower the pressure, if you lower the temperature, especially if you lower it close to the boiling point, because again, that's the lowest temperature gas can be in, because if you go lower, it becomes a liquid. So, near the boiling point, the there will be a very significant attraction between particles, which means that the pressure exerted on the walls of the container will be uh, much smaller than predicted by the ideal gas state. For gases held under identical conditions of pressure and temperature, helium, nitrogen, methane, and ammonia, rank them from least to most deviation from the ideal gas behavior. So here you will speak about size and intermolecular forces. So for NH3, you've got hydrogen bonding, that's the strongest possible bond here, and a pretty large molecule. So that's the highest deviation from the ideal gas state. Then you've got CH4, so London dispersion, but a pretty large molecule. And then N2, and then helium as the smallest and the weakest intermolecular force. Is pretty clear and a good question. The graph shows PV divided by nRT plotted against the three gases. This is similar, almost the same. No, I actually think it's exactly the same graph that we had in the example. So helium, nitrogen, carbon dioxide, identify which curve is which. So the curve that deviates the most is CO2 because it's got the strongest intermolecular forces and it's the biggest molecule, right? And then the green will be N2 and the helium will be the most similar to the ideal gas state. Conditions for most nearly ideal behavior. A student must choose conditions under which a sample of methane will behave as nearly ideally as possible. So which of these conditions presented here is the closest to the ideal gas state. So, and as we said, this should be the one with the highest temperature and the lowest pressure. And of course, that would be D, right? And there's a nice overview here. Why? At a 1 mole sample of a gas is confined to zero point 0.5 liters at 300 kelvins. The pressure measured in the container is 42 atms. Calculate the pressure of the ideal gas law and see which state is dominating. So, what do they want to say? So, we will calculate the pressure from PV equals nRT. And if we do that, we get that the pressure should be 49.2 atms. However, the pressure is actually 42, which means the pressure that we measured is lower than the pressure that the ideal gas state dictates, which means that intermolecular attractions dominate, because when intermolecular attractions dominate, then the pressure is lower, right? The volume effect at very high pressure. So at very high pressure, the volume occupied by real gas is found to be larger than the ideal gas law predicts. Explain why. So this is an opposite example. So you can see an explanation here. So at very high pressure, actually the volume is of the particles is significant. So since the particles now have significant impact on the volume, that volume, the whole volume of the gas, will actually be higher than if this gas were in the ideal state. Two samples of the same gas are held at the same moderate pressure, 400, one at 400 K and the other one at 250 K, just above the temperature at which the gas condenses. So this is just above the boiling point, right? Which sample deviates further from the ideal behavior and why? And you can see here, I mean, obviously 250K will be closer to condensing than 400K. It's a pretty easy answer. Okay, let me know if you need any help and good luck. Bye bye.